Hello everybody. In this video I'll be going over sort of the kinematics continued. This time we're going to talk about accelerated motion. And so everything that we had previously talked about was non-accelerated motion. We might have touched on acceleration a little bit, mentioning that on a displacement time graph, if we see a curved line, that's an indication of a changing slope. And because the slope is, or the gradient of a displacement time graph gives velocity, when we see evidence of a changing slope or a curved line, that's evidence of a changing velocity, which we said was acceleration. So there's sort of a preview of the idea. Acceleration is a changing velocity. But it's still part of kinematics, which remember is a study of motion without regard for what's causing that motion. As I record this, there's obviously not a link to the video covering these slides, but I'll be sure to sort of update that before I post this assignment. And your weekly assignment, remember, is just keep a record of all the work that you're doing in a physics journal there. Send a picture by noon, Friday, every week to my email of just all the pages of your journal. Your lab work's going to be included in there, your definitions, practice problems, the record of all of your work there. So keep that in mind. All right, the learning objective, and let me just say that you may not have completed all of the learning outcomes from non-accelerated motion. It's okay to spend a little bit more time if you need to add more practice problems in, and you'll see that physics, we sort of build ideas up. So we'll continue to see, definitions of displacement. We'll continue to add vectors, certainly. Acceleration is a vector. In fact, that's one of the ways that we'll define it here. And so don't feel like you had to have mastered, everything from the non-accelerated motion chapter. I'm uploading this set of slides for those students that feel prepared to sort of move on to the next set of learning objectives. And here they are: to define acceleration, to draw and interpret velocity time graphs. So remember, we had a similar learning objective to draw and interpret displacement time graphs from the previous lesson. We're going to derive and use the equations of uniformly accelerated motion, describe a method for determining the acceleration due to gravity g. Hey, we'll describe a couple of methods for that. And explain projectile motion in terms of horizontal and vertical components of motion. And hopefully from all the vector addition that we've been doing, this idea of the horizontal and vertical components, that makes a little bit more sense. All right, so to define acceleration, we say it is a vector quantity. It's equal to the rate of change of velocity, and we measure it in meters per second squared for the SI units. And so it's the change in velocity divided by the change in time. That's what acceleration is. So speeding up or slowing down. It's also important to note that we could maintain a constant speed and simply change our direction, and that would also be an example of acceleration, because remember, velocity is a vector quantity. So if we change our direction, we're also changing our velocity, even if we maintain the same speed. So like if you're rounding a curve in your car, you might usually slow down, but if you just maintain the same speed, you're still accelerating because you're changing your direction there. And so that's important to keep in mind also. Draw and interpret velocity time graphs. And so if we look at a plot of velocity against time, we can kind of think about it as we're starting out at a speed, a velocity of 0, and then here we're increasing our speed. And so that's what we call acceleration, right? We're accelerating or changing our velocity. And then the motion of the object who's represented by this graph here, it just sort of goes to a constant velocity, right? And so we're not changing our velocity anymore. So somebody like who sped up to a certain speed, maybe the speed limit, and then it looks like they're slowing down here, and so they're going, sort of their velocity is decreasing. So that's sort of labeled on the plot there. The distance traveled is the area under the graph. You may recall from the previous lesson that we said the area under a displacement time graph has no physical meaning, but the area underneath a velocity time graph will actually tell us the displacement. So the total distance traveled is going to be the area underneath this graph. So if it's a curve like this, it's sort of like a trapezoid, and you might know a formula to measure the, to discern the area underneath, or the area of a trapezoid. We could easily break this down into, sort of more familiar shapes like triangles and rectangles and things like that. And so the distance traveled is the area underneath the graph. The acceleration and deceleration can be found by finding the gradient of the lines. And so there's two really important ideas: that we find the acceleration by finding the slope of a velocity time graph, and the area underneath the curve there on a velocity time graph gives the displacement. Here we see another velocity time graph where the object is starting at a velocity of 0, and then after 1 second moving 4 meters per second, after 2 seconds moving 8 meters per second, and so it's uniformly increasing the velocity as a function of time. So that every second the object is going 4 meters per second faster. If we were to find the slope of this, we would say that it's rising 4 meters per second every second. So 4 meters per second squared would be one way to report the value of the acceleration, the object whose motion is represented by this graph here. To derive and use the equations of uniformly accelerated motion, we're going to consider a velocity time plot, and I've actually taken the liberty to prepare a separate video where I've kind of worked through the derivation of all of those equations of uniformly accelerated motion. So go ahead and either at this time right now, go ahead and click the link and watch that video as many times as you need to. Have paper and pencil ready, like I'm sure you do right now as you're taking notes, and be prepared to pause it, rewatch it as you need to. So I sort of go over, there's 4 equations and they're on the subsequent slide, but you're going to want to know, where do they come from? What is the derivation of them? And so take a look at that video either now, or you could always finish this video and then make sure that you go back and watch that one deriving what we call the big 4 equations of motion. And they are here. So the big 4 equations of motion relate 5 different variables: acceleration, final velocity, initial velocity, the time taken, and the displacement. And any given equation, will sort of omit one of those variables. And so we'll typically call this first one here equation 1, v equals u plus at. So the final velocity equals the initial velocity plus the product of the acceleration and the time. This equation solves for displacement. The displacement is equal to ut plus 1/2 at squared. The displacement can also be calculated by 1/2 u plus v times t. And the equation that doesn't contain the variable time is v squared equals u squared plus 2as. And so there'll be plenty of practice problems that will need these equations of uniformly accelerated motion to solve. It is an important point to note that we can only employ these equations when we know we have a situation of uniformly accelerated motion, because these equations are derived from a graph like we saw on the previous slide, where we just have the gradient is constant, it's not changing. And so we have to keep that in mind, that we only apply those equations if we have this sort of a situation where we have uniform acceleration. For the lab work over the next several weeks, we'll do experiments where we can determine the acceleration due to gravity, what we call local g, and it's usually a lowercase g is the variable used to represent that. And so it's sort of the strength of the gravity field. And so here on Earth, where we do our physics experiments in high school, we want to be able to conduct an experiment that's going to tell us how strong is the gravity field, sort of here on Earth. And so we'll do an experiment with free fall, where we'll be dropping objects and seeing how Earth's gravity field can accelerate those objects. And we'll also look at doing an experiment with a pendulum, where we allow a pendulum to oscillate back and forth, and the strength of the gravity field does affect the time period of oscillation for a pendulum. And so we can use the physics underlying that to determine the strength of Earth's gravity field, what is called local g. I'll tell you right now that the sort of known and accepted value is around 9.8. And in ACE physics, we're always going to use g equal to 9.81 meters per second squared. And so that's saying that on Earth's gravity field will accelerate an object that's sort of falling in it 9.8 meters per second faster every second it falls. And so that's about 22, 23 miles per hour every second. So every second something falls, it picks up about 22, 23 miles per hour of speed. And so gravity fields accelerate things, and we can kind of measure the strength of that gravity field in terms of the acceleration due to gravity. The final learning outcome associated with accelerated motion deals with projectile motion. It says to explain projectile motion in terms of horizontal and vertical components of motion. If we look at this figure here, we can see that projectile motion is when we sort of launch something into the air, and we've got things going on in the y direction and things going on in the x direction. So when something is launched in the air, it may have a component of its velocity that's going upward. Like you throw a ball in the air and you're sort of exerting a force upward, so the object will accelerate in that direction, and it has, sort of the fastest it's ever going to go is right when you sort of throw it into the air. Because you can see from these red vectors here in the y direction and the vertical direction that the velocity is decreasing. And that's because, remember, we just talked about Earth's gravity field is an accelerator and accelerates things in the down direction. So if you throw something up in the air, Earth's gravity field is going to slow it down until eventually it's probably going to reach a speed of 0, and that's the point sort of right at the top of the parabola, the vertex up there. And then it's going to speed it back up in the opposite direction. And so the constant acceleration of Earth's gravity field is going to slow things down until they reach a stop in the y direction, and then speed them back up, going down again. And you can kind of see that represented by these red vectors on this figure here. The blue vectors, you may notice, don't change their magnitude. And that's because gravity doesn't speed things up or slow things down in the horizontal direction. So the combination of accelerated motion in the vertical direction and non-accelerated motion or constant velocity in the x direction gives us this shape, this parabola. So if we were to sort of, draw the resultant between the blue and the red arrow at any one of these points, we'd see that it would sort of trace out this path that the object actually follows, which is a parabola, like, somebody kicking a football there, or, a golfer teeing, off on a golf ball. So there's plenty of examples of projectile motion, and it's the same physics that we understand here on Earth for, launching projectiles, and we'll be able to calculate how far away projectiles, land, how long they're in the air, and we'll look at, applying some of those equations of uniform acceleration to projectile motion. That same physics, allows us to launch rockets and, send, rovers to Mars. So the power of understanding this physics is something that we harness every day in our society, and how awesome that is shouldn't be lost on us. So I will upload specific videos that cover this learning objective, similar to how I did for the equations of uniformly accelerated motion, where we'll look at lots of practice problems involving projectile motion, as well as using those equations of constant acceleration to solve things like, how high up will something go if we launch it at a given speed, at a given angle? How far away will it land? Those are the sorts of questions we can answer related to projectile motion. But in terms of explaining it in terms of horizontal and vertical components, as the learning objective asks, we can simply say that we have, in the vertical component of motion, acceleration, because that's the direction that gravity acts in, and the horizontal component of motion, there's non-accelerated motion, again, because there's no gravity there. And we're assuming that wind resistance is negligible. Now, the air that sort of an object may be crashing through here on Earth can actually exert a force and decelerate things, in the x direction. But for now, we're just going to kind of say that all of those effects are negligible until we're prepared to really deal with, wind resistance when we study forces. So that's just a quick overview of all of the learning objectives associated with accelerated motion. Do indeed make sure that you go back and take a look at the video on deriving those equations of uniformly accelerated motion, as well as a few of the videos that I've uploaded that are just sort of like some of the big ideas in physics, like a concept map, that kind of explains a lot of the quantities that we're going to study in mechanics, as well as the units that we measure them in, sort of the big ideas of vectors and scalars that we've been talking about. And be on the lookout for other videos related to some of these learning outcomes. As always, if you have any questions, please don't hesitate to reach out. Have a good one.